Alright, thanks for watching, and today I want to show something really cool. I want to tell you how to get the solutions of y double prime minus 5y prime plus 6y equals 0. So constant coefficient differential equations with two distinct roots. Usually the way it's presented is you suppose your solution is of the form e to the rt and you mess around with this, and then at the end you say, oh, e to the 2t plus b e to the 3t. But first of all, in my opinion, it's very hand-wavy. Why would you even guess that your solution has this form? And more importantly, how do you know that all the solutions are of this form? What's nice of the method I'll present is I actually show you from scratch how to solve this. And by the way, this is not my idea. I think David Nadler at UC Berkeley came up with this, and I T8 for them. So I remember this idea. It's really cool. And it's just based on the idea of differential operators. So define d as follows. D of y is just y prime. So it's the linear transformation which takes y as an input and spits out y prime. And notice you can actually write this differential equation in terms of d's. It's the same thing as d squared, d squared minus 5d plus 6i y equals 0. What does that gibberish mean? Well, d squared, that's dd. So d squared y is dy double prime. Minus 5d, that's minus 5y prime. And I just means do nothing. So 6iy is just 6y. And the amazing observation is you can actually factor this function out. So we get d minus, let's say 3i times d minus 2i y equals 0. So the reason we have this auxiliary equation, it's really just to factor this operator out. And now here's a cool thing. Let's call this z. Then it turns out z satisfies a very easy differential equation because we just get d minus 3i z equals 0. So z prime minus 3z equals 0. So z prime equals 3z. But this we can solve. It's a first order differential equation, and if you want, divide by z, integrate, etc., etc., and you get that the solution of this is z of t equals a e to the 3t. That is good because we solve for z, and using that we can solve for y. Because what do we have? D minus 2i y equals z by definition. So y prime minus 2y equals a e to the 3t. And it turns out we can solve this as well, and it's just this neat idea of the integrating factor. Let's multiply both sides of our equation by e to the minus 2t. And then we get e to the minus 2t times y prime minus 2y equals a e to the 3t e to the minus 2t. And then e to the minus 2t y prime minus 2 e to the minus 2t y equals a e to the t. Don't worry, the solution will not be e to the t, so it's just something that helps us. And in particular, what's nice about this, notice we can recognize this as the product rule. The Prada rule. Yeah, because indeed that's the same as the derivative of y e to the minus 2t prime. A e to the t. So all we need to do is integrate this. So y e to the negative 2t equals a e to the t plus some constant. And by the way, if there's a kt here, the 1 over k gets swallowed in this a. So it'll still be the same constant. And then lo and behold, we have y of t multiplied by e to the 2t. So a e to the t e to the 2t plus b e to the 2t. And then we get y of t equals a e to the 3t plus b e to the 2t. And what are 2 and 3? They're precisely, if you want, the roots of, if you want, r squared minus 5r plus 6. That's why for the auxiliary equation we need to solve for the roots. And generally it's heuristically explained by just guess your function, but it's actually really a question about factorization of operators. And there you go, you have your solution, and in fact those are the only solutions there are. Alright, I hope you like this extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.